The serial clock, it has the clock, master in, slave out, and master out, slave in. Okay, so, and the chip select signal. It's a 4-wire communication protocol, and it is based on clock, so it is synchronous communication protocol. Okay, it's widely used for short distance communication, primarily in embedded systems. Like usually, like you can transmit data for 3 meters, but SPI, SPI and I2C are recommended for transmission within the PCB, printed circuit boards. Okay. So serial, it is widely used for short distance communication. The one disadvantage of SPI is it needs an additional chip select signal. So when you interface more number of devices, you need additional GPIO for choosing that. Whereas for I2C, by using 2 wires, you can connect up to 1008 devices. Okay. So and only in SPI protocol, like only one device can act as a master. The rest of the device are slaves. Whereas in I2C, any device can act as a master and the rest of the device can be slave. Okay. Whereas in SPI, only one master and multiple slaves. So master and slave mode. So so this is the connection, like a serial clock will be connected to the serial clock of the slave. Okay. Master out, slave in is master out is the it's a transmitting side, transmitting of the master, whereas it is input of the slave. And master in, slave out is the receiver input. Okay. And SS is for slave select. It should be active low. The bar represents active low. So this is for multiple slaves. So this is the master. Like you can connect serial clock. You can choose these slaves by using this GPIO pin, by using the slave select. By enabling to enable the slave select, you have to drive the pin low. Okay, if you drive the pin low, like you will enable the slave select, and you will choose this slave 1. If you want to choose slave 2, then you have to enable GPIO to low signal. You have to give active low signal to this device to select. Okay. So this is the circuit diagram. We are going to use ADXL345, the same thing. So in the previous case, we use only the SCL and SDA for I2C. If you want to use it for the SPI, you need 4 pins. Okay, SCL and SDA and SDO. So SDA is master out, slave in. Okay, SDO is master in, slave out, and CS for chip select as a slave select, chip select or slave select. ADXL345 should be the slave. Okay, should be the slave, and you have to configure STM32F411 as master. Okay, and you have to give ground and 5 volt. So let's go for the program. Let me open STM32 QBIDE. So I'm just opening STM32 QBIDE. So I'm just going to copy the previous program. Okay, I just copy the previous program. Right click, copy. Okay, and right click. I'm going to paste, and I'm going to change this as SPI. Okay, SPI. So I check for the source file. Okay, so these are the files which we have written on the day. So let me remove all the I2C functions. All these symbolic names are related to ADXL345. So I'm not going to remove this. So this is related to I2C. So I just remove this. Okay, I just delete all the symbolic names which is related to I2C. I also delete these functions. Okay. So I just go to the bottom and I just remove all the functions which is related to I2C. Okay, so this I have only the definition. Like I'm just going to remove all the functions here. Functions related to I2C. Okay, so the rest of the function I just keep. I save the program. Right click. I just build the project. Okay, so I'll show you I'll explain the code one more time, like what I have done so far. Like I have copied this project which was done on the previous class, and I use the symbolic names for the ADXL345. These are the symbolic names of ADXL345. I just keep it as it is. I have removed all the symbolic names which is corresponding to I2C. I have also deleted the function prototype related to I2C, and I have also removed the functions. Okay, delete the functions. So I just have only the functions which is related to ADXL. Okay. Now the first thing you have to do is you have to open the data sheet. Okay, you have to open the data sheet. You just go for page number 15, like the functional block diagram. You have to choose from this block diagram, you have to choose the SPI. So we have SPI1, SPI4, SPI5 is there, then SPI3 and SPI2 is there, okay? So out of this, I'm going to choose SPI1, okay, SPI1. It is connected to APB2, okay, Advanced Peripheral Bus 2, okay, whereas the previous I2C one is connected to Advanced Peripheral Bus 1. This is to Bus 2, APB2. The next thing you have to do is you have to check for the alternate functions. Okay, you have to check for the alternate functions, and you have to find out which GPIO it has the SPI1. So you have to check from the data sheet. It's page number 47. It is SPI1 master and slave out is connected to PA6. SPI1 SCK is connected to PA5. Okay, PA7 is SPI. It is connected to master out slave in. So it is connected to PA. So I'm going to use PA7, PA6, PA5, and PA4. Okay. Okay. I'm going to use. So I just open the program. Okay. And I'm going to configure here as, let me configure as master in slave out as PA6. Okay, it is, I'm going to master in slave out. I'm going to connect to PA6. Okay. And master out slave in, it is PA7. Okay, master out slave in is PA7. And clock is PA5. Okay, and chip select is PA9. Okay, and we have AF05. Okay, we have AF05. Alternate function is the AF05. So the first thing is to so we need to initialize. So I just create a function called void SPI underscore init. Okay, SPI underscore init. GPIO underscore init. Okay. Okay, so SPI underscore GPIO underscore init void. Okay, the first thing is we need to set the RCC register. You need to set the RCC register. Okay, RCC. So AHB, it is connected to AH. So you check from the data sheet. Okay, so GPIO is connected to AHB1 ENR. Okay, AHB1 ENR. It is Advanced Peripheral Bus 1 equals GPIO AEN. Okay, GPIO AEN. So you have to create a symbolic name for this. Okay, it is the 0th bit. So hash define. Okay, unsigned, one U stands for unsigned, so it is 0. Okay, so you have to create a symbolic name for GPIO AEN. Okay, so it chooses 0 because from you have to get that value from the data sheet. Okay, if you check the value of the data sheet from the general purpose input output, okay, registers click GPIO port mode registers. Okay, sorry, it will be on the RCC register. Just go for RCC register. You have to enable click RCC click RCC. Okay, RCC registers. So in RCC register, you have to go for AHB1 ENR. The register name is Advanced High Peripheral AHB1 ENR. Okay, enable registers. Okay, AHB1, it is GPIO-AN. So here it is 0. Okay, so you have to enable this to enable GPIO-A. So we have done this in the previous class. Okay, so I have enabled this GPIO-AEN. So the next thing is you have to configure the mode. Okay, so the mode is you have to configure the mode as chip select is output, whereas you have to use the alternate functions like you have to use PA5 for the alternate mode. Okay, have to set PA5 for SPI. Okay, for SPI, you have to choose the alternate mode here, alternate function, alternate. So GPIO-A. Okay, so the motor is the register. Okay, you have to set that to 0. If you want to set to 0, okay, it is 10. This is to set 0. Set 0. You can find, I'll tell you, like, I'll show you how to do this. Okay, motor, this is to set, this is to set 1. If you want to set 1, okay, to set 1. This is for PA5. So you just open the data sheet, click GPIO port mode registers. Okay, so this is GPIO port mode register here. Port mode register. Here it is 10. The alternate function mode is 10. Okay, so we have to choose PA5. PA5 is here. Okay, so you have to set 0 for this and 1 for this. Okay, so this is the pin number here is 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, it starts from 0. Okay, it is 10. It starts from 0, it is 10. And for this bit, you have to set 1. It is 11. Okay, so it is 10 for, you have to set 0. For 11, you have to set 1. Okay, similarly, you have to copy and paste this for PA6 is the next one. Okay, so this is 12 and this is 13. Okay, for PA7, copy this. PA7, set PA7 for alternate mode. It is 14 and 15. Okay, once you set this, then you have to set PA9 as output pin, because PA9 is for chip select. Okay, for PA9 for slave select. Okay, slave select. So it should be configured as GPIO. Okay, output. It should be configured as output mode. Okay, so for output mode, you have to configure this as output 011. Okay, it should be configured as 1. It should be 0. Okay, Okay, so the number here is 9 actually. So 9 means it comes around 18 and 19. 18 and 19. Okay, this is to set slave select to set the output mode. All this GPIO should be for the alternate mode. The alternate, because alternate function is SPI. Okay, so we have to set that for alternate function. This is the code for setting. 0, 1 is the code for setting that to alternate function. So we have set PFI to was 1 0. Okay, now you need to set the alternate function registers. Okay, you need to set the alternate function register like GPIOA. So AF, it comes under AF for 0. Okay, okay. This is 21, this is 22, this is 23. So you have to check the alternate function registers. Like if you want to check, you go for GPIO registers. In GPIO, you check for the alternate function registers. Configuration, alternate function low registers. Okay, here. So this is the alternate function low register. Here it is, we have to set AF5. Okay, AF5 is 0101. Okay, so you have to set, so we are using PF5. So PFI 0, 1, 2, 3, 4, 5. PFI is here, is 20. It starts from 20. For 20, you have to set 1. Okay, 1, 0, you have to set here for 21. For 22, again 1. And for 23, 0. You have to set 0, 1, 0, 1 here. Okay, so that is 20, 21, 22, and 23. And we are setting, this is 1, 0, 1, 0. Okay, we have set this one. This is for PF5. So you have to set this. This is to set PA5. Okay, alternate function for PA5. You have to set the same thing for PA6 and for PA7. Okay, this is to set PA5. You copy this. This is for PA6. Okay, and this is for PA7. So 20, 21, 22, 23. Here it is 24, 25, 26, 27. Okay, here it is 28, 29, and 30. Okay, 30, 31. Okay, so we have set the alternate function registers. Okay, so that's all about the GPIO initialization. The next is we have to configure SPI config. Okay, I just create a function called SPI config. You have to enable the, okay, you have to enable the RCC register, like you have to enable the APP2 ENR. Okay, yes, you have to enable the SPI 1 enable. Okay, you have to create the symbolic name for this. Just go for hash. Okay, okay, so it is from the data sheet. You have to get this value. So this value is, you have to check for this value for is 2. Okay, you need to check this value from the RCC register. Go for RCC register, click RCC register. You have to check for the AHB1 ENR. Okay, APP1 ENR. Okay, so ABB1 ENR. So here it is SPI1. You have to check for SPI2 is there, SPI3 is there. You have to check for SPI1. This is ABP1. Okay, so but ours is it is on ABP2. So you have to check for the next register, ABP2. Okay, here. So here it is 12th bit. Okay, it is 12th bit. So you need to give in the program, like you have to set the 12th bit. Okay, sorry, 12th for SPI. So we have enabled the SPI, like we have enabled the clock for the clock access. We have enabled clock access, enable clock access for SPI. Okay, SPI1, and you have to set the clock. Set clock. So you have to go through SPI1 registers here. Okay, and you have to create the symbolic names. So let me open the data sheet. Go for the SPI registers here. Okay, you click the serial peripheral interface register, SPI registers here. Okay, okay. So I have opened the SPI control registers. Okay. So you have to create the symbolic name for this. So clock, okay, baud rate control is FP clock divided by 4 is 001. Okay, it is 001 FP clock. You have to set the, so I'm going to use the baud rate control is FP clock by 4 is 001. So it's from, so I'm going to set the clock. So it is on CR1 register, SPI CR1. Okay, CR1 stands for control registers. So let us set the clock for the SPI. So I'm going to use FP clock. So our clock is 16 megahertz. So we are going to divide that by 4. So SPI1. Okay, you have to take the CR1 registers, and you have to set the first bit is 1. Okay, 3. This is 4th is 0. 4th is you have to set as 0. Okay, this is 4 and this is 5. We have set the clock. Okay, set the clock, and you have to set the C pole polarity and C pole to 1 and CPHA to 1. The register CP pole to 1 and CPH to 1. Okay, it is 0 and 1. So it is in the data sheet. Like you can open the data sheet, CPOL, okay, and CPHA. So CPOL and CPHA are the clock polarity. Okay, you have to check. You have to set the clock polarity and master selection. Okay, bit 0 is for clock polarity and CPHA is for master selection. It means you have to enable STM32F411's master and ADXL is slave. Okay, so for that you have to, for master configuration you have to set 1, and for clock polarity we have to set 1. Okay, to polarity is 1. You have to set clock polarity to 1. You have to set 1 here. So that's the reason we have chosen, like we have set 1 here for the clock polarity, and this is to select this master. This is for selecting as a master. Okay. Master is, sorry, clock phase. Okay, clock phase and clock polarity. So master is 2. Okay, master is 2. So this is to select this is master, you have to give this is 2. Okay, master phase, this is clock polarity and the clock phase. Okay, this is to set master, to set as master, set as master. So the next is you have to enable full duplex, enable full duplex, and enable, you have to set MSB first. Okay, so for that, copy this. For full duplex, you have to set the 10th bit as 0. Okay, you can check to, like, for, okay, so receive only. So for full duplex, if you want to make full duplex, you want to give 0 for this. Okay, for bit 10 you have to give 0, that is full duplex. Okay, for bit 10, this is for bit 10. Okay, and we have given 0 for make it as full duplex. Okay, and next is set to set MSB first. Okay, so to set MSB, like MSB is bit 7. Okay, so you have to set 0 to transmit MSB. I just copy this, put 7 here. Okay, set 7 to transfer MSB first. Okay, so you have to set 8-bit data mode to set 8-bit data mode. Okay, 8-bit data mode. So 8-bit data mode, 8-bit data mode is it is bit 11. Okay, data frame format, 0 for 8-bit, 1 for 16-bit. So we have to give 0 for 8-bit, so it is 11, bit 11. Okay, and you have to select software slave management. Okay, select software slave management. For this, the bit is 8 and 9. Okay, 8 and this is 9. Okay, and finally SPI enable. I'll show you. It is 6. Okay, so just go through the data sheet. SPI register, like you go for bit 6. Bit 6 is SPI enable. You have to give 1 for peripheral enable. Okay, and for software slave management is 8 and 9. Okay. Slave select and software slave management. Okay, so to enable this, you have to give 1. 9th bit is 1, and 8th bit is also 1. Okay, so we have given the 8th bit as 1, 9th bit as 1, and SPI enable is 6. Okay, so we have completed the code for the config. Let me compile the program. I click build the project. We got 2 errors. Okay, I click build the project. Okay, so is now let's write function for SPI transmit and receive void. Okay, void SPI underscore transmit. So our function is going to take 2 input arguments. One is the pointer variable of data. Okay, the other is the size. Okay, size. So I'm just going to create a variable for uint 32t 32 underscore t of I equals 0. Okay, so uint 8 underscore t temp. So while of I less than size. So I'm going to transmit until we have the information. So you have to check for the it's same as like it is same as like I squared C. We have to check for the SPI1, okay, SPI1 status register. We have to check for the status register with the status of the TXC transmit enable. Okay, the transmit enable is set. Okay, if the transmit enable is set, then it should be hang on. Okay, so this transmit enable, you have to create a symbolic name for this. So you could create the symbolic name for transmit enable. Okay, it is hard to get from the data sheet. Of 1. Okay, so this one, it will be on the in the data sheet. You just go for the SPI registers. Okay, SPI registers, you have to check for the SPI and I2C registers. Out of this, you have to check for the status register. This is control registers. You have to check for the status registers. Okay, this is control register, status register. Okay, this is the status register, SPI underscore SR. So TXC, RXNE, and like OBR, okay, BC. So these are all the thing. These are all the. You can create the symbolic names for this registers. So I'm going to create like TXC is 1. Okay, TXC is 1, RXNE is 0. So let me create so that we can use it appropriately on our code. So TXC is 1. Okay, so I'm going to copy this, paste it here, and put this as RXNE. Okay, RXNE is 0. Okay, and SRBC, it is 7. Okay, you can get from the data sheet like BC is 7. Okay, BC is 7. Okay, BC is 7. And you have TXC, RXNE, BC, and the other thing is multi-byte. Okay, so multi-byte enable. So this value also you have to get from the data sheet, multi-byte enable, and read operation. Okay, so read operation is 80. So these two values you have to get from the data sheet. Okay, so we have declared the symbolic names. Okay, now let's go for the program for the functions. So TXC, so you have to wait until you got the TXC. Okay, then write data to the register. Okay, write data to the register like SPI1. You have the data register is data of I. Okay, I plus plus. Okay, so we have write the data. You have to wait until TXC is set. So this is to wait until TXC is set. If TXC is set, then you write the data to the register. Write data to the data register. Okay, So you have to check again for wait until the TX is set. Okay, and you need to check for this. Okay, so you have to wait here, wait until, and you have to set wait until the busy flag is set. Okay, until the busy flag is set. If it is set, then you have to clear the overflow flag. To clear, you just have to read this value. Read the read SPI1, okay, from the data register. Okay, so you could get this from the data sheet, like you check for error, okay, or overflow. Okay, so you could check here error handling. Okay, so you have to just read this. You have to just read this twice, okay, to clear the overflow flag. This is just to clear the just to clear the overflow flag. Okay, you have to read the data registers and status registers. You have to read from data register, the other is from the status register. Okay, so once it's read, like, so this while loop is closed here. Okay, so it is extra. So right click, build the project. Let me check for any error. Oh, sorry. So right click, build project. Okay. So we have completed the function for the SPI transmit. Okay. Then we need to create a function called SPI receive. Let me cross check once. Okay. Okay. So let us create a function for SPI receive. Void transmit. This is for receive. Okay. So while of size, we are going to read while of size. We are going to read SPI1. Like we need to send some dummy data. Okay. For dr equals, so SPI1 dr equals 0. Okay, and you have to wait until the RxNE flag is set. You copy this. Okay, if it is else, you need to move for data. You can equals SPI1. You can read the value from the DR register. Okay, how to use. Okay, so we have completed the function for SPI receive. Right click, build the project. Okay, again 2 errors. While of size, right click, build the project. Okay, so the next is we need to write function for void cs enable. Okay, this is a function. I'm going to copy this GPIO-B. So the ODR register, it is PA9. Okay, and to enable, you have to make it low. Okay, you have to make it low. Okay, this is for enable. For disable, I just copy this. I'll change this as disable. This is okay. So this is enable and disable. Okay. So I'll copy the function prototype on the top. Okay, so GPIO init, SPI config. So copy all this function prototype on the top. Okay, SPI receive and SPI transmit. Okay, so we have, let me check, right click and build the project. Okay, so we have created all the functions, create functions, SPI receive, transmit. Now we need to use it. Let us go and modify the ADXL init. So ADXL init, you have to copy these two functions, SPI config and SPI. Okay, I'll just copy this to function to okay. So I have initialize. Okay, this is not required. The rest of the function is same for the previous one. So ADXL init is done. So ADXL okay. So the next is ADXL read and ADXL write. Okay. So ADXL read address. So here I'll change this as ADXL read here. Instead of registration, it should be address, and we need to add the data also, 8_t of the pilot RX data. Okay, this is to, because we'll be reading 6 values. Okay, RX data. So here you have to check, set the read operation. You have to set read operation. So in order to you copy this address, okay, as read operation. Enable you have to enable the enable multi-byte. Okay, enable multi-byte. So I just copy this. Okay, so now you have to enable the CS. Chip select. Okay, now you can start transmitting the address. Transmit of, this is address. Okay, this is the size. So SPI, you just receive RX data. Okay, and this is the size 6, totally 6 values. X, Y, X, because X will be splitting 2 values. X for X not on X1, Y not on Y1. So totally 6 values will be there. Okay. And once this is finished, you need to disable this one. Okay, disable. So ADXL read is there, ADXL write. Okay, that ADXL read, ADXL write. There's no need of read values. So for ADXL write, okay. So uint, I just declare a local variable, uint 8_t of data 2, okay. And you have to enable multi-byte. Have to enable multi-byte. Okay. So data 0 equals address. So it should be address here. Okay. Address. Okay, and data 1 is value. This is address and this is value. Okay, so to write, you need to enable and disable. Okay, copy this, paste it here. You transmit the data here. This to. Okay, so right click, build the project. RX data. Okay, RX. Okay, right click, build the project. Okay, so we have built the project successfully. Let me connect the kit and I will show you let me check whether it is working or not. it should read the values. Okay, so right click, go for debug as STM32 Cortex application. Choose SPI ELF, click OK. It will ask for switch. Okay, click OK. It will switch for debug mode. No stealing director. Okay, so let me connect the kit. Okay, I just connect this kit. Let me try again. Right click, go for debug, SPI ELF. Okay, click OK. So I have downloaded the program inside the kit. Let me switch for debug view. Okay, so these are the expressions. I have made the connection as per the circuit diagram. This one, as per the circuit diagram, I have made the connection. So now now it should read the values. So I just put a breakpoint here. Okay, and just try to run the program. So it's telling like the value we are getting is 0 here. Okay, it is getting 0 here. It means so we have some problem on the code. Let me check for the program. So first is ADXL init. Okay, ADXL init SPI config. So right format is right. Everything is okay. So let's go for ADXL write. ADXL write is address. Okay. This is value CS enable. Okay, so SPI transmit. It is okay. ADXL write is okay. ADXL read. ADXL read. Let's check for ADXL read is read operation multi-byte. It is also okay. Okay, it is also okay. So ADXL write is checked. Let me check for SPIO unit. Let us check for SP. Let us initialization of GPIO. Okay, SPIO GPIO unit. This is GPIO AEN. Okay. So mode or 10 and 11. Okay. This is also okay. Okay, so it is also correct. Config pin is so correct. C1U01. Okay. Set as master. Before that, let us enable as duplex here. Okay. Okay, so there is no problem on the data mode. Config, there is no problem on config. Like everything seems to be right. Let's check for the transmit. Okay, we had done a mistake here. It should be GPIO-A. I don't know how I mentioned this B. right click, build the project. So there will not be any enable on this code. So right click, debug as STM32. Okay, click OK. Switch. So I give resume button. We should get some values here. Like again, there's some problem there. Okay, let me we should get a value here, but we are not getting the value. So still we have some problems. Okay, let me check. Okay, so we have not called the function here. We have to data underscore rec. Okay, okay, so now it should work. I click build the project, debug as STM32. Click switch. Okay, so I just click the run button, resume button. Okay, you could see the values here. Now I try to move the accelerometer now. Okay, you could see the values changing now. So you could try from your end. With this, I close the session. Thank you so much for your time. See you in the next session tomorrow. Until then, bye bye. Take care.